Hello everybody. In this video I have some basic vector exercises which hopefully will help you especially when you're trying to find the components of a vector, which is a very important step before you can manipulate vectors. So these exercises that I'm going to show you are taken from the workbook that comes with your textbook that you can buy, that is associated with your textbook. This is not required material, of course, but it has very useful exercises, which actually in face-to-face classes I use pretty much every day that we meet. I do a few exercises during class, so if you want to get it, I do recommend it. So let's take a look at this one. This is exercises 10, 11, and 12. It says that that they want you to draw and label the x and the y component vectors of the vector shown. So in exercise 10, you can see that there is a vector A, and we need to draw and label the x and the y component vectors. So what is the x and the y component vector? So imagine that you're illuminating this vector with a light bulb from the left. So when you do that, you can assume that you're going to have a shadow of the vector of this arrow, that there is going to be a shadow forming on the y-axis. So if you draw that shadow, that is what we call the y component vector of A. The y component vector of A is the shadow of the vector on the y-axis. If we do the same thing, but now illuminating the vector from above, then we're going to get a shadow on the x-axis. The shadow of an arrow looks like an arrow, so the x component vector of A looks like an arrow, but as you can see in this particular example, is pointing to the left. Now students tend to, when they're asked to draw the x or the y component vectors of a vector, they skip putting the head to the arrow, and this is actually a mistake that that leads you in some situations to make errors regarding the minus or the plus sign that the component is going to have. So please make sure that when you draw the x or y component vector, you actually draw a vector, and vectors always have the head to make it into an arrow. So this is for that vector A. Notice that the x and y component vectors of A, when added together as vectors, they form the original vector A. The projections of A along the x and the y-axis, when added together, not as number but as vectors, they give you the vector A. Again, this statement that we just have there, it's valid for vectors when you're adding vectors. Remember that you don't add vectors just like you add numbers. You don't have a vector of magnitude 3 plus a vector of magnitude 5. It's not going to give you a vector of magnitude 8 necessarily. That's not how you add vectors. So careful with that. You can see that the x component vector and the y component vector, when added together, gives you A, because, well, you can use the parallelogram rule, right? You take the two vectors that you're adding, you put them tail to tail, you complete the parallelogram, and the sum vector is the vector that goes along the diagonal. You practice that in one of your computer lab activities. So another way to see that the x component vector and the y component vector, when added together, they give you A, is to use the tail to head method. So you can take the vector AY and put its tail touching the head of AX, and the vector that goes from the tail of AX to the head of AY is the vector A. So clearly A is AX vector plus AY vector. All right, let's do another exercise here. So this is vector B, so you can see in the third quadrant, and we want to draw the x and the y component vectors for B. So let's start with the x component vector. So that is Bx vector, and when we project this vector on the y-axis, we get By vector pointing down. Again, don't forget that these must be arrows. You're drawing the component vectors are arrows. The arrow representing By component vector points down. The arrow representing Bx component vector points to the left. this is going to have a consequence in terms of the x and y components being negative for this vector. We'll do more of that in a minute. Let's do another one. Let's say that vector c is as depicted in the picture. So what is the x component vector for c? Well, when you project this vector on the x-axis, you obviously get the same vector because the vector is fully on the x-axis. So the x component vector of c is the same as the vector c, and clearly there is no y component vector for c, so it is equal to 0. All right, in the next three exercises, we're going to determine the numerical values of the x and y components of each vector. So the first exercise has a in the second quadrant, magnitude of 5 units, and they're showing us there that the angle that a makes with the positive x-axis is 130 degrees. So they want you to calculate the numerical values of the x and y components of each vector. So notice that in this exercise, we're not dealing with the same quantity or the same physical quantity that we dealt with in problems 10 to 12. 10 through 12, we were dealing with the x and the y component vectors. They were asking you to draw those vectors. In 13 through 15, they're asking you to calculate the numerical value of the x and y components. So what is the difference? Well, first of all, ax and ay, what we're going to calculate here for ax and ay is going to be some numbers, positive or negative, but they're numbers. So what is the difference between ax and ax vector? In other words, what is the difference between the x component of a and the x component vector of a? Same for the y. What is the difference between ay and ay vector? The difference is actually significant. So the way the x component vector is defined is that the ax vector is a number multiplied by the unitary vector I hat. So remember that I hat is defined as a vector along the positive x direction of magnitude 1. So if we have another vector that is also horizontal, then that x component vector is going to be a multiple of I hat. So ax component vector is a number multiplied by I hat. The number is what we call the x component. So that is the number that we're looking for in problems 13, 14, and 15 to find how much is that number that when multiplied by I hat gives us the x component vector of a. Notice that, so the difference between ax and ax vector is that ax is a number and ax component vector is a vector, because I hat is a vector. So a number times a vector gives you a vector. Again, that number ax could be positive or negative. It would be negative, for example, if the x component vector pointed to the left. It would be negative because I hat is always a vector pointing to the right. So ax is a multiple of I hat, but that multiple is a negative multiple. For example, if ax was 5 times as big as I hat, then ax component vector would be minus 5 times I hat. All right. The same goes for the y component vector of a. So ay vector is ay times j hat. So that's because j hat is a unitary vector in the y direction. Ay component vector is the part of a that points in the y direction. So it is a vector that is vertical. So it must be a multiple of j hat. And that multiple is the number ay that we're looking for. So that number is positive or negative. And ay component vector is a vector because it is equal to a number multiplied by a vector. So that gives you a vector. So again, it's a number that could be positive or negative. Negative will be the case, what you will get when the ay component vector points down, for example, because j hat is always pointing up. So ay must be a negative number. All right. So after that clarification, we can calculate ax. Let's take a look. So first of all, draw the x component vector first. See what it looks like, in what direction it points. So when you do the projection of A on the x-axis, you get a vector that points to the left. AX points, component vector points to the left. So the number that we are going to be using here will be the adjacent of that angle of 130 degrees is obtained by taking the magnitude of the vector, or the hypotenuse of the right angle triangle, which is 5, and you multiply by the cosine of the angle, in this case 130 degrees. So 5 times 130 degrees gives you minus 3.21. So that is your x component of vector A. The minus sign, notice that the calculator, when you put in cosine of 130, the calculator also gives you the answer as a negative number. So check to see if it makes sense. Take a look and see that AX is a component vector, points to the left. As we said, since I hat points to the right, AX must be a negative number. So that negative number is correct. This is what we expect, given that AX component vector is opposite to I hat. So that minus is correct. For the AY component, draw the AY component vector. That vector ends up pointing upwards. So the magnitude of that vector is the same as the magnitude of this line that I'm drawing on the left hand side. And you can see that that is the side that is opposite to 130 degrees. So the AY is 5 times the sine of 130 degrees, which gives you 3.83. Notice that the sign is positive, and as you can see, since AY is pointing up, then that's the sign that we were expecting. So it should be positive. That's correct. All right, moving on to 14 and 15. So in 14, we have the vector B in the third quadrant, making an angle of 30 degrees with the negative x-axis, and the magnitude of B is 4 units. So we're looking for Bx, the x component of B. First step, as always, draw the x component vector of B. So that x component vector is an arrow that points to the left on the x-axis, so pointing to the left. So the magnitude of that arrow is going to be the hypotenuse multiplied by the cosine of 30 degrees, since Bx is the adjacent of 30 degrees, so that goes with cosine. And notice that there is a minus sign that we have to put by hand, because we know that our answer needs to be a negative number. Bx is a negative number, because Bx component vector and I hat are pointing in opposite directions. For By, we have the y component vector pointing down. The magnitude of it should be the same as the length of this side of that triangle. That is the opposite side to 30 degrees. So By is going to be obtained by the hypotenuse 4 multiplied by the sine of 30. And again, we're going to have to put the minus sign by hand, because we know that By is pointing in a direction opposite to the direction of j hat. So it must be a negative, By must be a negative number. And the numerical value is minus 2. All right, moving on to vector C, fourth quadrant, 45 degrees with the positive x-axis, magnitude of 5. What is Cx? So we start by drawing Cx vector. Points to the right, as you can see. The projection of the vector on the x-axis points to the right. Therefore, Cx is 5 times the cosine of 45 degrees. It is a positive number, so this is correct. Cx points to the right, so it's a positive number multiplied by I hat. For Cy, we get a component vector that points downwards. The magnitude of that component is going to be given by 5 sine of 45 degrees. And we need to put a minus sign because Cy is pointing down. It's opposite to j hat. The numerical values are 3.54 and minus 3.54. All right, now at this point, some of you might be comfortable with all these calculations. But some of you might be wondering, or you might not be sure, when to use cosine, when to use sine, when to put a minus sign in front of the cosine or in front of the sine. So let me work on that a little bit to help those students. So we're going to do a few more exercises to figure that out. So let's start with this vector A. So A has a magnitude of 5. Notice that the angle of 30 degrees is between the y-axis and A. So we're looking for AX component and AY. So would you say that AX is 5 times the cosine of 30? Well, that is actually incorrect. Start by drawing the x component vector to see that this is not going to be true. That is not going to be correct to use the cosine of 30 degrees. So AX component vector looks like that. So we know that AX is going to be a positive number. The length of that component, is the same as the length of this line that I drew up here. How long is that line is the question. Well, this is the adjacent side of the angle 30 degrees. And the length that we're looking for is the opposite side of 30 degrees. What that tells you is that AX is going to go with the sine of 30 degrees, because opposite refers to the sine trigonometric function. The hypotenuse multiplied by the sine of the angle gives you the length of the opposite side. So AX in this example is going to be given by 5 sine of 30 degrees, not cosine of 30 degrees. The positive sign is because, as we can see, AX is pointing to the right. What about AY? Well, for AY, let's start by drawing the AY component vector, the projection of the vector on the y-axis. Notice that that falls on the adjacent side of 30 degrees, and adjacent is given by cosine. So AY is going to be 5 cosine of 30 degrees. It is positive again, because as you can see, AY is pointing up, which is the same as the direction of J hat. All right. Another example. Let's say that A is pointing this way, also magnitude 5, and the angle for A is given by 145 degrees from the positive x-axis. So what is AX? Do we use sine of 145 or do we use cosine of 145? So again, maybe at this point you're catching on the idea that I want you to always first, before you do any calculations regarding the components of a vector, I want you to always take the extra 2 seconds to draw the x component vector and the y component vector. So the x component vector of A points that way. Notice that it's pointing to the left. It falls on the adjacent side of 145. That means that we're going to use the angle of 145, but the cosine of it. The hypotenuse is 5, so we're going to have to multiply this by 5. And now you might be asking the question whether you need to put in a minus sign or leave it like that for this component. The answer is, this is just right the way it's written, 5 cosine of 145. Notice that if you put in your calculator cosine of 145 degrees, you'll get a negative number. You are expecting the x component to be negative, because notice that the AX component vector points to the left, whereas the I hat vector points to the right always. So they're opposite to each other, there has to be a minus sign, or the x component needs to be a negative number, but cosine of 145 already gives you a negative number. So there's no need for you to put the minus sign by hand. If you were to put a minus sign in front of the 5, the whole quantity will be a positive number, AX will be positive, and that would be wrong. AX has to be a negative number. So 5 cosine of 145 is correct. The reason why you're not having to put or fix this, put a minus sign, is because the angle 145 degrees is measured from the positive x-axis, and it is also measure in the counterclockwise direction. When that is the case, there is no need to fix the sign that your calculator is going to give you. It should be correct. All right, for the y component, draw the AY component vector. It's pointing up. The length of it is the same as the length of this line that I'm drawing on the left hand side of your picture. That closes the angle of 145, or is the opposite of 145. So that means that we're going to be using a sine of 145. Again, you can check that the sign is correct. Sine of 145 in your calculator will give you a positive number, and we are expecting the y component to be positive, so this is correct. All right, another example. Let's do the same vector a 5 units, second quadrant, but now notice that the angle is 45 degrees as measured from the negative x-axis. So using that angle, how do we express ax? So draw the x component vector. Looks that way. Notice that it fell on the adjacent side of 45 degrees. So we're going to use cosine of 45. The magnitude of the vector is 5, so we need to multiply by 5. And is it positive or negative? Should it be positive or negative? It's got to be negative. That's because the cosine of 45 is a positive number. But looking at our picture, since we have our ax component vector drawn there, we know that it's pointing to the left. We know that our final answer must be a negative number. So we put the minus sign by hand in this case. So why do we have to put it by hand in this case and not in the previous case? The reason is that the 45-degree angle was not measured from the x-axis, from the positive x-axis. It is measured from the negative x-axis. So since it wasn't measured from the standard positive x-axis going counterclockwise, you always have to check to see if the sign that you get is correct. All right, last example here, a 5 units, the angle is 150 as given in the picture. So how do we calculate ax? All right, so draw the ax component vector. It points to the left. The magnitude of the vector is 5. The x component vector falls on the adjacent side of the vector of the angle 150 degrees. So since it's the adjacent side, it's going to be cosine of 150. The magnitude is 5, so 5 cosine of 150 should be the ax. And consider the sign. Should it be positive or should it be negative? So cosine of 150, the cosine of any angle bigger than 90 and less than 270, you know, is negative. So cosine of 150 is going to be a negative number. Are we expecting the x component of a to be negative? Yes, so that is correct. We don't have to put an additional minus sign. 5 cosine of 150 will give you a negative final answer. That is correct. For the y component, draw it. It points downwards. Therefore, we're expecting that component to be a negative number. Let's put in, so the magnitude of the component should be the same as the length of this side, which is the opposite of 150. So we're going to go with 5 sine of 150. Now sine of 150 is a positive number. Are we expecting the y component to be negative? We already said that it should be negative, but 5 times sine of 150 is not a negative number. So we're going to have to fix that by putting a minus sign, again by hand. So why do we have to do that? The angle of 150 that they gave us was measured from the positive x-axis. So why do we need to fix that sign of the y component by hand? We didn't have to do that for the 145 angle that was in the picture above that one. So why do we have to fix it in this one? Well, don't forget that this 150 degrees is measured in the clockwise direction. It is measured from the positive x-axis, that's good. but it is measured in the clockwise direction. The angle that we would have to use if we didn't want to fix any signs by hand, we would have had to use the angle measured from the positive x-axis but going counterclockwise. So that would be 210 degrees. So if you had used the 210 degrees, then the x component would be 5 cosine of 210. No need to fix the sign because that will give you a negative number. And the y component would have been 5 sine of 210, again giving you the correct negative answer. So again, it's important that you keep in mind that you might need to fix the sign of your components, x or y components, depending on what angle you're using. So what's the bottom line? You might be wondering, okay, so do I need to fix the sign by hand? What's the bottom line? Well, the bottom line is, if the angle is not measured from the positive x-axis and counterclockwise, then you always need to check to see if the sign for each component that you're getting in your calculation is correct. How do you know if the sign that the calculator gave you is correct? Well, you need to first of all draw the vector, obviously. Second, you need to draw the component vectors, that is the x component vector and the y component vector. Only by looking at those component vectors you can tell what a sign are you expecting. Are you expecting the x component to be positive or negative according to your picture? So this is an essential step. Another question, do I use sine or cosine? What's the bottom line? Well, to answer this question, again, you need to draw the vector, you need to draw the x component vector and the y component vector. Now let's say that you are wondering if for the y component you need to use the cosine or the sine of the angle that they're giving you. So you need to ask yourself the question, does the AY component vector fall on the adjacent side of the angle? If it does, you're going to use cosine of that angle. If it falls on the opposite side, then you're going to use the sine. You might continue to wonder, well, okay, cool, but what is the adjacent side? So let's go over that again. The adjacent side is, first of all, draw the vector A, draw the x and the y axis. There's going to be the angle that you have, it's always going to be given, or is going to be defined by the angle between the vector and either the x or the y axis. So the adjacent side is the axis that is contributing to form the vector. One side of that angle is the vector itself, the other side is going to be an axis. That is the adjacent side of the angle. So if you're looking for or wondering about the y component of this vector, notice that the y component vector falls on the y-axis, which in this example is the adjacent side of theta. So that tells you that when computing the y component of the vector, you're going to be using the cosine of that angle theta in the picture. Let's take a look at another one. Let's say that your vector A looks like this, and the angle theta is measured between the negative x-axis and the vector. So what is the adjacent side of theta? So it's the side that is not the vector, is the axis that is not the vector A, so that's the adjacent side. The x component vector of A falls on the adjacent side. Therefore, to calculate the x component of A, you're going to be using the cosine of that angle theta. Now, remember that the positive or negative, the sign, you're going to have to evaluate that, but we already discussed that. So you need to determine whether you're going to use cosine or sine, and also you need to determine whether the final answer should be positive or negative, and fix the sign if the calculator is not giving you the right sign. All right, last one. So vector A in the third quadrant, angle theta specified between the positive y-axis and the vector, which is the adjacent side of theta. So the adjacent side of theta is the y-axis. If you needed to compute the x component of A, notice that the x component of A falls on the x-axis. That's by definition the x component of A. So the x component vector of A does not fall on the adjacent side. It's actually perpendicular to the adjacent side. Therefore, the x component, which the length of which is the same as the length of this arrow that I'm drawing here, that is the opposite side of theta. So AX is the opposite side, falls on the opposite side of theta. Therefore, to calculate AX in this example, you will be using the sine of theta. All right, that's all I have. I hope that is useful. I'll see you in the next video.